This video is just an introduction to the basics of multiple regression. So multiple regression, as opposed to simple regression, just means that we have more than one explanatory variable. So let's do the sort of smallest possible addition to something you've seen before, which is you saw a regression of daughter's education on mother's education in the simple regression slides. Here we're going to add father's education to the regression model. So this is our outcome. We now have two explanatory variables and the unobservables u here. We have the same sample of about 2,300 daughters in the PSID who can be linked to both parents' education. And when I include mother's and father's years of education, you can see the coefficients here. Okay. So this is an example of an estimated regression line or equation right here. Notice the education hat there means it's a predicted or fitted value. You can see down here the R code for this. So the thing to notice relative to what you've seen before is inside the LM function here, you have your outcome Y, and then you have one explanatory variable, the next explanatory variable, just separated with a plus. And you can imagine extending that plus x3, plus x4, etc. All right, so in general, the syntax is Y is being related here to, this is your first x variable, second x variable, and so on. All right, interpreting the estimates. So this, you saw a very analogous slide in the simple regression slides. In the model, notice there are three variables on the right-hand side, x1 and x2, your explanatory variables, and then everything else is in the unobservables u. So when you interpret the coefficient on x1 here, we are holding fixed everything else on the right-hand side, x2 and u. That's what it means to hold all else fixed. So we're isolating what we might call the partial effect of x1 on y, right? Holding these other variables fixed. Okay, that's how to interpret beta 1, the parameter in the model. When we actually estimate the regression and get this estimated regression equation you saw an example of on the previous slide, by definition, the unobservables are things that are not going to be included in the regression, all right? So when we interpret the coefficient on x1 here, now we would say it's the relationship between y and x1 holding fixed any other explanatory variables in the model. So here that's just x2, okay? So one of the things that's very useful about multiple regression is we can hold fixed or control for other explanatory variables, but we can't control for everything that way, right? Because we're still not controlling for the things that are in the unobservables. So we might say something just in general, like the beta 1 hat, the coefficient on x1, the estimated coefficient, is the change in our predicted y when the associated x sub 1 here, increases by 1 unit, holding fixed any other explanatory variables that are in the regression. So in this case, just x2. But again, remember, still, when you're looking at these regression estimates, you're not holding fixed the unobservables. A lot of the things from simple regression carry over in a really straightforward way, just extended to the multiple regression case. So you've already seen the model, you've seen a version with like 2 explanatory variables. This is a version with k explanatory variables, okay? So just kind of a general version here. The estimated regression equation is what we get when we use our sort of our estimates, the beta hats that we get from OLS, okay? Plug those in here, right? Of course, the unobservables are not in the estimated regression, and so that gives us a predicted value of y based on our estimates of all the betas and then the values of the explanatory variables. A fitted value is just the same thing, but plugging in specific x values. So for example, if we said in the intergenerational persistence of education example, the mother and father have a certain amount of education, what's the predicted value for daughter's education? And then the residual, ui hat, is still the actual y minus the predicted y. That's the main thing to remember on this line. All right, actual is y sub I, predicted yi hat. Right. The R squared is still defined as the share of the total variation in the outcome y that we can explain with our regression. Right. So this is variation in the fitted values y hat. This is variation in the observed y sub I. And the R squared is just the ratio of those things. As you add additional variables to a regression, the R squared cannot decrease There's an edge case where it stays the same, but in practice, the R-squared increases as you add variables to a regression. And part of what that should highlight for you is that maximizing your R-squared is typically not what you're trying to do in a regression. Okay, so again, just think of it as a measure of goodness of fit, to be interpreted sort of carefully. Okay, one last slide here, and that is how do we get our estimates? Well, it's still by the least squares principle, okay? And that least squares principle is minimize the sum of the squared residuals, right? So now the residuals here, actual minus predicted, and when we plug in that long expression for a predicted or fitted value, that entire term inside the parentheses here is now the residual for observation I, that's ui hat. We're going to square the residuals, we're going to add them all up, right? So now this becomes our sum of squared residuals, and the OLS problem is to minimize that by choosing all the beta hats, okay? But unlike the simple regression case where we could actually, in principle derive and at least write out the first order conditions, and then you could imagine how you might solve a system of 2 equations and 2 unknowns, here there's a system of k plus 1 equations, k plus 1 unknowns, right? Because there are k slope estimators and the intercept estimator as well, okay? So you would kind of need linear algebra to express and solve the system, and that's beyond the scope of what we're going to do. All right, so that's the basics of the multiple regression model.